Hi, my goal is to provide an intuitive first understanding of the architecture that has taken the world by storm, the transformer. The architecture can look intimidating at first, but I hope to clear up some of the most confusing parts. This technology is progressing at such a fast pace right now. The amount of scientists entering the field needs to catch up so we can keep moving forward in a safe and responsible manner with diverse ideas and perspectives. My goal is not just to get something to work, but to interpret at each step the why for a non-superficial understanding. In order to give an intuitive technical understanding, I must pair our interpretations of the model with code. At the end of the day, many people will have different interpretations of the same technology, and the only source of truth is the code. When attempting to summarize these complex subjects, the essence can easily get lost in translation, especially when those complex subjects require you to reason about higher dimensional spaces, as we will be doing today. So we cannot rely on others' interpretations. We must see these discoveries expressed as code firsthand. The code we are looking at today is from Andrej Karpathy's brilliant Zero to Hero series and is linked below. Andrej Karpathy was a founding member of OpenAI, then head of AI at Tesla, and I think he's now back at OpenAI. He has blessed us with wonderful lectures that I've linked below. He starts with a step-by-step spelled out explanation of backpropagation and training of neural networks, and takes you through to finally building a small GPT from scratch. Andrej is a wonderful human being who gives back by producing awesome educational resources and who inspired me to make this video. I went through his series and I want to share with you how I am able to make sense of some of the abstract thinking required. I will help you see some of the intuition behind the matrix math. For example, we see matrix addition used a lot across several different contexts, like positional encoding, biases in linear layers, and residual connections. How do we make sense of this operation? What is the difference between matrix addition and matrix concatenation as occurs in multi-head attention? My first question when trying to reason about these was, how does just adding numbers together provide the model with the information we think it does? We will dig into these types of questions. Now let me quickly mention, if you find this video may be valuable to others, please click the like button and share to help propagate my lecture forward to those who might need it. Okay, let's begin. So the 5-second interpretation of a transformer is, or my 5-second interpretation, is a transformer is a model that learns to generate data similar to what you fed it. And that's simple enough. So let's figure out how. So we will first go through a high-level overview. This is not yet the structure of the transformer itself. We will briefly look at the model as a black box for now, so we can interpret the input and output. You may already understand some of these prerequisite ideas, but just bear with me, we will ramp up in a sec. I will try to be really quick here because I want to get to the meat. A lot of this part is common to all of deep learning and is not transformer specific. Okay, so with the high-level overview, it is very important to know how the model is used, because if you don't, then it becomes hard to reason why it's structured the way it is in the first place. So first, we have this text data. We must represent it as something the model can train on. So the very first thing we do is encode the text data. You might already be aware of models like ChatGPT. They work on text at the subword level, which means they encode their text data into tokens, which could be full words or subwords. If you want to look more into this, I've attached a link to the encoder that OpenAI uses called TickToken below. But our text, let me just go to the code. Our text data will be encoded at the individual character level. Our text data is 1 million characters of Shakespeare. Here we read in all of that Shakespeare text, and we see the first 1,000 characters of it here. So we want to encode it. So our encoding function is very simple. Each one of the characters that appears in our text that you can see here is going to be represented as a number 0 to vocab size -1, which in this case is 0 to 64, since our vocabulary size is 65. So here you can see we encode some text and then we decode that encoded text here. So our first step is to encode the entire text data. So now after that we have a tensor full of integers. And quick note here, you can see that we split up the data into training data and validation data. This is so we don't overfit our model to our data. What happens here is that we take 10% of our data and not let the model train on that data, so that after training and during testing, we can test the model on data that the model hasn't seen before. Okay, now our data is a TensorFlow of integers and ready to be passed into the model. But we don't just pass in the whole text. What our model will take in instead is many different little parts of this body of text. We define a context length and then grab that many characters from a random offset into our text. Let's say our context length is 8. So let's see an example. We grab this segment from our text and we added one more character at the end because this serves as the target character given these 8 characters, and I'll explain why that is right here. This doesn't just serve as one example. We're given these 8 characters, this one character is likely to be next. It actually serves as 8 individual examples. What our model will see is this follows this character, 56 follow these 2 characters, 57 follow these 3 characters, and so on. So with just this one segment, we have 8 examples that our model is going to be learning. So you can see it follows this context or X to target or Y fashion. And down here, we are just making things more efficient by simultaneously looking at 4 independent examples, which we call 4 batches. So instead of working with a single row of 8, we have 4 rows of 8. And we can do this because the operations performed on this data when going through our model are very simple. So we take advantage of our hardware by asking our model to not just look at one example for one training step, but for each training step, we're looking at 4. And they are all independent of each other. It's not like the learning is across these 4 independent examples. Okay, so this is really useful. We input the data in this way into our model, and we do this thousands and thousands of times or steps. And our model learns from these examples. This is the training process. So let me go to the paper that introduced the transformer architecture. And let's scroll down to a diagram of the architecture here. So now let's lose the black box mentality and think about the transformer as a string of layers. Each of these layers have weights. Think of weights as knobs that, when tuned, help the model behave in the way that we want it to. But how do these weights know how to tune themselves? All of these weights know which way to go, up or down, because of the constraint we impose on the transformer at its very last layer. And it's not obvious in this diagram, but this very last layer redefines the goal of the transformer to a simple mathematical expression to minimize loss. So note, we have restated our goal of the transformer from our 5-second interpretation to generate data similar to what was fed in, or aka predict and output highly probable words, to simply be minimize loss. Minimize loss just means in order to be less wrong, we have to be more right. Remember how we have our input in the fashion it's in, that is, it's in this like context or X to target Y fashion. This allows our model to easily grade its own predictions because we can use the measurement of negative log likelihood. Negative log likelihood is a measure of the difference between our model's predicted probabilities and the actual outcomes. So negative log likelihood is our loss function. This loss function is differentiable just like every operation in each layer of our model. So we can use backpropagation to guide how each and every weight in our model should be updated. I won't get into the nitty-gritty of backprop, although I would say it's definitely a prereq, and to watch the previously mentioned Andrej Karpathy series on this, where he explains it very well with code. With that said, I will still briefly say what backprop is doing at a high level, but remember, don't take this as a solid understanding, and make sure to go through Andrej's series linked below to become, as he puts it, a backprop ninja. Okay, backprop is simply the use of the chain rule from calculus to calculate the gradient of our loss function with respect to the model's weights. Why do we want to do this? The gradient is just the derivative of the loss function with respect to the weights. So it points in the direction of steepest ascent, or the direction in which the function increases most quickly. And this is incredibly useful because we want the direction where the loss function, instead of increases most quickly, where it decreases most quickly. Because remember, we want to minimize loss. So all we do is multiply the gradient by -1. So each and every weight of the possible billions of weights in our model now has the direction to go in order for it to do its small part in helping the global effort to minimize loss. For each weight, we just do weight equals weight plus, so whatever the weight previously was, plus gradient times 0.0001, which is known as the learning rate. So after the direction is known, it's pretty much just saying, okay, we're going to slowly update it in this direction. And so remember how I said to think about the transformer as a string of layers. Backprop starts from that last layer, or the output layer, and it will propagate gradients back all the way to the very first input layer. Because what's happening when we have all these layers connected, and behind the scenes in PyTorch there's this compute graph of the operation starting from all the way from the beginning, and it goes through all these transformations. So we have this nicely laid out compute graph to perform backprop on. And so we start from the last layer, and we're able to propagate gradients back all the way to the very first input layer because of the way the derivatives are calculated in the chain rule. That last layer is where we have all the information to start calculating the gradients, and then you have the information to calculate the gradients for the layer before, and then after that, you have information to calculate it for the layer before that, and so on. So now you understand that training is the process of optimizing these weights so that we get our model to output what we want. The weights of all these different layers in our model are slowly but surely moving in a direction to minimize loss. Okay, now that we know how the model is used, we can break it apart and look at each individual layer in our string of layers. So let's start with embeddings. So let's go down. Okay, right here. So right now our characters are encoded as integers from 1 to vocabulary size, or 0 to 64, because we have 65 different characters found in the Shakespeare text. This actually won't be good enough for the model to learn the meaning of each one. It is harder to see why at this character level, so pretend we are working at the word level for a second, like ChatGPT. So we're working with words instead of characters. So instead of a vocabulary size of 65 characters, we are working with a vocabulary size of, say, 50,000 words. So each word would be represented as a unique number, 0 to 49,999, let's say. The problem is you cannot compare words and see how they are similar to each other because each one has its own dimension. So in that 65 character example, pretend like here's a vector of all zeros, 65 zeros, and you have a 1 in like the 34th spot. That represents one word, right? This is a very, very unscalable way of representing words. Instead, we want the words to share dimensions, and these dimensions act as features of different words, and it's like a scale of how much for this feature, even though we don't know what each feature means, like the model is learning it. So not only can you not compare words when you're doing it in this way, when new words and word sequences not seen before come up, you have no way of knowing how to treat them because once again you cannot compare them. This is called the curse of dimensionality. Now, instead of allowing words to occupy their own dimension, so we go from a 50,000 dimension space to say a 30 dimension space. This is known as a distributed representation, and now words are forced to share dimensions in order to represent themselves. Think of each dimension as a feature, like I said, and along each of these 30 features, each word is on a scale for how much it has this feature. Now we don't know exactly what each feature is finding, but we can imagine. It is hard to visualize a 30 dimension space, so let's go back to the character level and see what a neural network could learn from going from a 26 dimension space for 26 characters in the alphabet to 2 dimensions. So going, like, let's say 26 dimensional space for 26 characters. So let's say you have a vector with 26 zeros. This is called one-hot encoding, by the way. It's a very simple representation where you have all these zeros except a 1 in the column that will represent that letter. So for example, if you have a 1 followed by 25 zeros, that would represent the letter A if the application that we're talking about is the alphabet. So instead of using one-hot encoding to represent an alphabet of 26 characters, what if we just use 2 dimensions to represent, and we have like these continuous numbers instead of just using an integer of 0 or 1? We have these continuous numbers that will be used in this 2-dimensional space. So now, before I show it to you, which letters do you think will be seen as very similar to each other? So you have A to Z, and just putting on in, like, just imagine 2 dimensions, X and Y. Which letters do you think a model would learn are very similar? So let me show you. And this is from a screenshot from Andre's series that I mentioned. We visualized this example. And you can see how the model learned that the vowels are very similar down here in the bottom left. A, E, I, O, and U, and sometimes Y. Pretty cool. So that is the basic idea behind embeddings, or distributed representations. They help models find how words are similar or different in a way that can be mathematically manipulated. You can learn more about this from the 2003 paper, A Neuroprobabilistic Language Model by Yoshua Bengio and company, linked in my description below. Now let's go back to the code. And go back here. Okay, so embeddings. So in.embedding is a simple lookup table. And we are saying for each of the words in this vocab size, so in our case, each character will have in embed many dimensions to represent it. And so I think we're saying that in embed is 32. So 32, each character will have 32 dimensions to represent it. So that's 32 features that the model is learning about each character. It works out perfectly that our current characters are represented with not just a number, but specifically an integer, 0 to 64, because this will act as an index into its own embedding representation. So remember how our input is structured in the way it is. It's just with our encoding, it just makes it a number 0 to 64. So that's what this is, and we're just passing these indices into our embedding table, which is just a lookup table. So, and I'll explain in a second what position embedding is. So we have created the embeddings for our tokens, and so the weights for those 32 different features for each token is randomly initialized, and the goal is for it to learn. Those are weights that have to be learned. And to retrieve each of the embeddings for each character, we just simply do this because this is a table and this is an index. So we effectively went from having indices or locations for a character's embedding to actually just be their embedding representation. So now we get several benefits from this. One, you will see in a second, we're now able to use dot product to compare words because we're working with vectors. We can do that now because each word is represented as an embed mini, or 32 floating point numbers. Yeah, a vector. Number two, it's very flexible and allows our model to gradually update these numbers and find where these different concepts or words should be, i.e. it allows semantically closer words to be closer together. So that's embeddings. And before we finally move on to the next layer, which is attention, there's one last thing to do to our input. We will see shortly that our attention mechanism actually doesn't have a notion of word position or word order. Rather, the attention mechanism's purpose is to understand the context of a word by looking at other words in the sentence. However, this mechanism does not consider word order and instead treats the sentence as a bag of words. So we need to add this positional information of our input to our input. We simply create another embedding table, position embedding table, with context size many slots, or block size, which is, we defined it as 8, remember from our examples above. So then by indexing into it with this torch.a range, it's just saying 0 to 7, the numbers 0 to 7s, we grab the 32 dimensional embeddings for each of those 0 to 7 positions. So now that's what pos_emp represents. We then add this tensor to our token embeddings, and now our resulting tensor contains information about both the token and its position. And this can be very confusing. At first I struggled with understanding how adding these numbers together can possibly cause the effect we want of merging this information together. But an easy way to think about it is as a bias that's learned, the positional embedding. We are nudging the token embeddings. We have these token embeddings vector right here in the right direction. So let's say we have our token embeddings vector pointing right here for a particular token. It can be biased to point to a location that gives it more of a position 3 kind of vibe. And with my hands it's like 3-dimensional, but this is like a 32-dimensional space, so I'm just arbitrarily pointing. But by adding this positional embeddings, we're saying we're biasing each column. So it could be, because we know that actually the most important part is we can do this because we know the structure of our input. We know that each column is a different position or time t equals 0. Remember earlier how we have the 0 to 7 slots. We know each one represents a different position. So we know that we're taking advantage of how our input is structured, so that by adding the positional embeddings, we're saying, okay, along column 1, across all of these examples, we are biasing it to become more of a position 1 kind of vibe, and then for position column 2, we're biasing it to be more of a position 2 kind of vibe. Okay, so now we are ready to enter the layer of the transformer with the attention mechanism. So let's get started with the goal of the attention mechanism. The goal is to find the token value to output for each of these 8 examples we have, based on looking at what the other tokens in each example are telling you, but not just what all the other tokens are telling me, only tokens that are giving me useful information. And let me sneak another thing in to also make sure we are only looking at previous tokens, not future tokens. Because remember what this has all been about, to predict that next token based on our context-sized 8 number of tokens provided. Okay, with that goal, let's list out what it implies we need. It implies we need 1, a new representation of our tokens that tells us what information the tokens provide. 2, a new representation of our tokens that tell us what information the tokens want. 3, an efficient way to compare these new representations so we can get some kind of scale for how much each token wants what each other token is giving off. Let's just call this the attention scores. And finally, 4, a way to use these attention scores to finally pick the token value to output. Well, good news, we are in luck. Since we are representing everything with vectors, we can use a powerful tool to grab all 4 of these, the dot product. The dot product of 2 vectors can be viewed as a measure of similarity between them. When taking the dot product between 2 vectors, you multiply their respective components together and then add this all up, resulting in a single number. If the 2 vectors are similar and they are sort of pointing at the same spot, this number, their dot product, will be very high. If they're dissimilar and they're not really pointing at this same spot at all, their dot product will be very low. Now, if only we had a way to calculate dot products between a large number of vectors. Lucky us, we do. It's matrix multiplication. So just as a quick little reminder, this is what that looks like. Matrix multiplication is just a series of dot products between the rows of the first matrix and the columns of the second matrix. resulting in a new matrix. Each dot product becomes its very own component of the new resulting vectors in this new matrix. Not only can we use matrix multiplication to accomplish number 3 above and calculate attention scores, since it's so good at calculating similarities with the dot product, but we can also accomplish 1 and 2 of finding new representations for our input. Matrix multiplication is just a simple linear transformation and can be looked at as arriving at a new location. So let's look at the code. Here is one head of self-attention. I'll explain multiple heads in a second. So we have 3 different linear transformations here. All in.linear is under the hood is a matrix multiplication. That's all it is. So for example, what this is doing, k equals self.key, see key is an in.linear. It's just a linear layer. So what happens here on this line is just x at w, where w is this linear layer's weights that it's learning. So the weights describe the transformation that our input, aka the embeddings, go through to get to their new respective space. And these weights are learned, and they start out initially random by the linear module. So that's all this is doing is, this is just creating, initializing those weights. And so then when we pass an input through the layer, it's just performing a matrix multiplication. That's what this looks like, but with the keys weights. Okay, so we have 3 different ones because, like we mentioned earlier, we want 3 new representations learned from our input. 1 for what the token contains. That's our K, that's our K right here. 1 for what the tokens are looking for, that's our Q, or query. And 1 for what the token's actual value is of what key says it contains, which is value and V. So now we have accomplished number 1 and number 2 above to get to our goal, those being 1, a new representation of our tokens that tell us what information the tokens provide, that's our K, and 2, a new representation of our tokens that tell us what information the tokens want, that's our Q. So now we can get number 3, an efficient way to compare these new representations so we can get some kind of scale for how much each token wants what each other token is giving off. We call this the attention scores. This is way in our code here. This C part over here just scales the result by 1 over the square root of the number of embeddings. Short explanation is that this scaling is necessary so that the dot products don't get too big and mess up subsequent training. But back to the main part of this line, Q matrix multiplies with K. So you know how we just applied a linear transformation on our input to get Q. As it turns out, we can perform a linear transformation on Q now with K, acting as our instructions to get to the new space. That new space being our attention scores. The result of this matrix multiply gives us a map where each token, it has a magnitude for how much it cares about every other token. But remember when I stated the goal of our attention mechanism earlier and said we actually don't want tokens looking at future tokens and only want tokens looking at previous tokens. While our current map is giving information on tokens looking at future tokens, but we can easily zero these out with a triangular mask. That's what this line does. And it's really easy to see how it works above here. If we go to, right here. So the link with the code is in the description, like I said. But here Andre demonstrates what the triangular mask is doing. It's very easy to see from this output here that the top triangular half is zeroed out, because you can think of it as, okay, if this was the first token, it shouldn't learn any information about the previous ones. Okay, and this is the second token. Okay, it can garner some information from the first one, and the third one can get from the previous two, and so on. So I don't want to dig too much into this specifically, as Andre did a good job explaining it. So I'll go back down. Okay. So coming back down, the next line is a softmax. This softmax just normalizes the values across the last dimension, so we can use it as a probability distribution. Right now, way is just arbitrary numbers describing how much each token should care about each token. We want to normalize it so that for each token, now we are saying, okay, we care about this token 20% and this one 45%. So just a way to normalize it, so for each token, the row adds up to 1. So then we want to induce this probability distribution onto our values v. So this last line finally accomplishes our number 4 from above, or a way to use these attention scores way to finally pick a token value to output. The dropout here is just, this is a dropout layer. It's just for regularization, or making sure we're not overfitting the model. I won't speak too much on this. I would just summarize it by saying it randomly drops out or sets to 0 a portion of output features of a layer. Well, in this case, this guy. This makes the model less reliant on any single feature and forces it to learn more robust and generalizable features. But yeah, anyways, that is our attention mechanism. It took a little bit for me to reason about, but I think it's beautiful how we can just say, oh yes, by the way, this key space exists and this query space exists, and this is how we get there. This is awesome, and how we will continue to make progress in this field, finding creative solutions. You have to be really comfortable sitting in abstractions and have an open mind. But back to learning. So this is one head of attention. We can scale this up by using multiple heads. Each head will just be finding different things. So here's how we implement multi-head attention. You can see here in this multi-head attention class, we set it up so that there are number of heads, each with head size, output size on the linear layers discussed above. So the head size is just describing how big these linear layers are going to be. And the num heads is saying, okay, the actual number of the heads. And you can see in this forward function, which is what's called when we pass the input through this layer, we are just running each head and then concatenating each head's results in the last dimension. It's important to note the huge distinction here between concatenation and matrix addition. Remember with positional embeddings earlier, we viewed that matrix addition as sort of like a bias. We added positional embeddings to the token embeddings because we knew that each column was a different position or time. T equals 0 for the first position, and so on. So that by adding the positional embeddings, we were saying, okay, along, say, column 4, we are biasing it to become more of a position 4 kind of vibe. So it is because we knew what the shape of our input represented that we could do this, that shape being BTC, where T is what I'm saying are the columns. In this case, with multiple heads of attention, if we just simply use matrix addition to add up the numbers on top of each other for all the heads, then we really wouldn't be taking advantage of finding new information. It would be like acknowledging that this first dimension in head 1 is for the same feature as the first dimension and all the rest of the heads 2, 3, and 4. And this is not what we want. So instead, we concatenate all of our info from our heads along the last dimension. That's what this dim equals -1 is. This, of course, means that our shape is different. So we project, and here's another dropout layer, but you can ignore that if you want. So we project it back into the shape that we're used to. It's just a linear transformation that gets learned. So now we allow all of our heads to find different things, and then we allow a linear layer to learn weights to transform us back to the shape we have been working with all along. So that's multi-head attention. Now we're going to look at the difference between encoder and decoder. We haven't mentioned this yet, but it's easier to see back in this architecture diagram. But before that, let me just quick note that self-attention just means that the keys and the values are produced from the same source as the queries. In cross-attention, the queries still get produced from X, but the keys and values come from some other source. So you can see here in our diagram, this is cross-attention. And in our code, we're actually not using cross-attention. So first I'll just briefly say, okay, this is an encoder, this is a decoder, and this is cross-attention because right here, we're getting keys and values from some other source, the other source being the encoder. So now we have to, okay, what is an encoder and a decoder? Encoder, so our code is just a decoder. Encoder in cross-attention is useful for language translation tasks, like going from German to English, for example. And our decoder is useful because we just want to mimic Shakespeare text. If our problem was one of language translation, then we would use cross-attention so that we could attend to all the words of an input sentence. Say, like if you were translating I love cats from English to German, then the input sentence I love cats would be over here. And we want to attend to all of those words. So the distinction is in no longer saying not to look at the future tokens or words that that was a rule for us in our attention mechanism here in the decoder. We actually want to look at the whole input sentence. So all an encoder does to accomplish that is removing that line of code that had that triangular mask that we put in our decoder. And so now you can note that this says in our decoder masked multi-head attention, and here it says multi-head attention for the encoder because so for the encoder you just take this guy back out. Okay, so we can see what we have left now in this little block is FeedForward and added norm. So let's go over what add in norm means first. So the add in added norm means to use residual connections. So let's go back to the block, or not back, but let's go to the block class. Okay. And it's found in this line right here and in this line. So this self.sa is our application of multi-head attention that we just learned about. You can ignore self.ln for now. That is applying layer norm, which is what the norm is in add-in norm. But pretend that's not here right now. Just pretend it's, okay, self.sax. Okay, the residual connection is this x plus. And I hope by now we've built up a pretty good intuition for matrix addition throughout this video. Remember, with positional embeddings, we viewed matrix addition as sort of like a bias. We added positional embeddings to the token embeddings because we knew, based on the way that our input was structured, each column of token embedding, or the T in BTC, was a different position. So by adding the positional embeddings, we were saying, okay, along with say like T along T equals 4, we are going to bias it to become more of a position 4 kind of vibe. The positional embeddings are going to learn these numbers so that it'll bias it to kind of be in this other location that gives it a more position 4 kind of vibe. Well, we can view residual connections as a kind of bias as well. Imagine if we didn't have this x plus, and imagine we are at the beginning of our training. So all the weights in this self-attention mechanism have just been initialized and need to be learned. Now this will work, but it will take longer. and in a lot of cases much longer, especially because we want to scale this architecture up. As you see, it's in a block class, which we will want multiple blocks of. So what we do is we bias this by saying, you know what, start here. Start with what we had instead of just transforming this x that we've gradually gotten to. And then effectively what's happening is the difference between the output and the input, aka the residual, the output of this and the input of it, the x, is being learned. The residual is being optimized instead of starting from scratch. So that's residual connections. It took me a while to kind of reason about it, but it's not so bad. It's just saying, you know what, instead of just starting here, we're saying, okay, no, you know what, we don't want to lose this information. You can start there. It's just saying, yeah, the weights will be different, but it's going to get there quicker because the difference between the output and input is shorter and easier to learn than trying to start from scratch. And I'll link the paper to it down below. Okay, the norm in add a norm is, like I said, is layer normalization. And layer norm is very, very important, but I don't have time to get into it today. A short summary that does not do it justice is that the statistics of the outputs of each layer need to be normalized, or else you will run into big trouble training deep neural networks. You want everything to be fairly homogeneous throughout the model with so many layers. Without centering the data with so many layers, the model can quickly get messed up. When I mean centering the data, centering the outputs of each layer. Because if you have so many layers linked up, then you can gradually just kind of these outputs can explode to infinity or squash down to zero. And you see this firsthand in Andre's series. Once again, he does a really good describing it. So please do your due diligence on layer norm. I'm sorry I couldn't squeeze it in today. Maybe I can make another video on it. Okay, and then lastly, we have FeedForward, which we saw in that architecture picture. So up until now, we have accomplished a lot. The tokens are now attending to the tokens which they need to in order to get what they want, but there is very little computation power on reasoning about this resulting information and finding patterns. We want to now put our resulting info through a multi-layer perceptron, MLP, which is exactly what our FeedForward class is. It's just a linear layer followed by a non-linearity, ReLU. Okay, I lied. Since we are multiplying this linear layer's output size by 4 for more dimensional power, we project it back to the size we need it to be in. And lastly, there's this dropout layer, which I mentioned earlier, is just for regularization purposes or making sure the model does not overfit our training data. Okay, so why are we doing this FeedForward? Why are we putting it through an MLP? We're doing this because we're saying this is the time to find complex patterns. Non-linearities are what transform our linear function into a model that can, in principle, approximate any arbitrary function. If we just had a stack of linear layers, it actually just collapses to a single neural layer in terms of representational power. It's not as effective at finding powers or at finding patterns. The non-linearity is what gives this model the power to do so. So that's FeedForward. Okay, so we've made it to the finish line, and now it's time to make the actual prediction. So if I scroll down here, so remember we discussed up to here, and then this self.blocks is just passing the result of this, so the embeddings information through to self.blocks, and we went through self.blocks, and that forward is just putting it through attention and FeedForward, and we'll just have multiple of these blocks. So there's one more layer norm for the output of self.blocks, and then we apply one more linear layer with the goal of this linear transformation being to produce a probability distribution over the size of our vocabulary. So in our case, 0 to 64. so that we have this probability distribution over the numbers 0 to 64, and we want to pick one of those numbers, which, remember, represent a character to output, which has been the goal all along. Okay, so how do we interpret the result of this linear transformation? We interpret them as log counts or logits, because right now there could be negative numbers in this resulting linear transformation. And in order to finish transforming this output to a probability distribution, we need 1, all numbers to be positive, and 2, across the rows, it must sum to 1. All right, that's how we make a probability distribution. So after, and this, what I'm about to say is all occurs in f dot cross entropy, so we can't see it. But what happens is we take those logits and we exponentiate them, which solves number 1, so now we have all positive numbers. We perform softmax, which solves number 2, which is just normalizing. Remember earlier we talked about softmax. It's normalizing it so all the rows sum to 1. So like that row can represent a probability distribution. And cross entropy also calculates the loss from our loss function of negative log likelihood, which we mentioned earlier. But to restate it, negative log likelihood is the average of the negative logarithm of the resulting probabilities from the softmax. It works perfectly as a measure of the difference between our model's predicted probabilities and the actual outcomes. Okay, so, and then we can see here, this is how you use the model. So this is in charge of training it, and now we want to use it, and you can see how it's used down here. I think like 2,000 tokens are printed out, so you can kind of read and see. It's all gibberish, but it looks pretty good. Gloucester, all the Beteldrine, for to his like thou Thoron. Yeah. So to recap, our 10-second interpretation. So let's say our data is a bunch of text. We turn words into something that our model can see and work with, vectors. Then we have a mechanism called attention, which learns a mapping of which tokens care about which other tokens and to what degree. We pass this information through a multi-layer perceptron to reason about this information. And when our model is done training, we use it to generate text and is able to use patterns it learned to randomly select highly probable words to output, given what it has currently output, or the last 8. I think this, I don't think the context size for this generation was like, I think it was like 16, maybe it was like 62 or something. But anyways, another important thing to say about this generate is notice how it only focuses on that last time step, because that's the only one we care about because keep in mind when it's training, it's like I said earlier, with that kind of segment of 8 characters, that segment of 8 characters is in itself 8 different examples for the model to learn. But when it's outputting down here below, it's always just kind of doing the next one. Okay, so let's see. So lastly, I just want to clarify one thing, the difference between pre-training and fine-tuning. As you can tell, what our code has given us today can sort of be looked at as some kind of document completer. It's really good at babbling on about something. This is pre-training. But in order to get something like OpenAI's ChatGPT, you need fine-tuning. That is the process of aligning this pre-trained model to a more question-answer structure that uses reinforcement learning with human feedback to accomplish that. Okay, conclusion time. So hopefully I gave you some intuition about these models. It's beautiful that we can just assert that these different high-dimensional spaces exist for a model, like the key space and the query space, and then observe the consequences. It reminds me of how we can change axioms in mathematics, explore those consequences, and discover new truths about the universe. A lot of abstract reasoning is required in this field. We need more creative, good-hearted scientists to progress further in a safe, responsible manner with diverse ideas and perspectives. I didn't have as much time as I wanted and was only able to do this in one go. I'm about to go on a cruise. But there's still so much more to talk about, and not just ideas to do with our example today. Personally, I like the intersection of attention and curiosity and exploratory problems and algorithms. This has a very deep analogy to my own life that I'll share one day. But for now, please let me know in the comments all your questions and also other topics you may be interested in. I may potentially do a video on it. Thank you so much for taking time to watch this. I hope you learned something and or are inspired to dig in deeper. Now let me end with a quote. They who really want to get to know something new, be it a person, an event, a book, does well to entertain it with all possible love and to avert their eyes quickly from everything in it they find inimical, repellent, false, indeed to banish it from mind, so that, for example, they allow the author of a book the longest start, and then like one watching a race, desires with beating heart that they may reach their goal. For with this procedure, one penetrates to the heart of the new thing, to the point that actually moves it. And precisely this is what is meant by getting to know it. If one has got this far, reason can afterwards make its reservations, that overestimation, that temporary suspension of the critical pendulum was only an artifice for luring forth the soul of a thing. Friedrich Nietzsche.